Hello. In this recording, we will do some example problems from Chapter 1. The objective is to know and be able to use the definitions of current and charge. The first problem that we will work on is example 1.2. No charge exists at the upper terminal of the element in the figure for t less than 0. So our current for t less than 0 is equal to 0 amps. And at t equals 0, a 5 amp current begins to flow into the upper terminal. Okay, I'd like to make note when the text uses the term upper terminal, they are talking about terminal 1. In an older version of the text, the ideal basic circuit element looks something like this, where the current flowed into the upper terminal, but they have since changed the basic circuit element to look like what we have here. So, moving on. Part A, derive the expression for the charge accumulating at the upper terminal of the element for t greater than 0. We know that current is the rate of charge flow. So our current equation looks something like this. And if we multiply by dt on both sides, we get an expression for charge, which is the integral of current I dt. And we want to derive an expression for charge accumulating at the terminal 1 of the element for t greater than 0. So for t greater than 0, we would put it in here, and Q of t is equal to 0 to t 5, and we'll change this dt since we have two of them here. We'll change it to dx. So this would give us 5x from 0 to t, which would be 5t minus 0, which is 5t coulombs. So Q of t, our expression for charge accumulating, is Q of t is equal to 5t coulombs. Okay, in part B, if the current is stopped after 10 seconds, how much charge has accumulated? All right, so now Q of t is 10 seconds, would be 5 times 10, which is 50 coulombs. Or we could substitute 10 in at this point, and 5x would be from 0 to 10 seconds would be 5 times 10 minus 5 times 0, which is equal to 50 coulomb. Okay, that takes care of this problem. Let's move on to assessment problem 1.3. Okay, the current at the terminals of the element in the figure looks like this. So the current is 0 for t less than 0, and it is 20 e to the minus 5,000 t amps for t greater than equal to 0. Calculate the total charge in microcoulombs, entering the terminal at its upper element. All right, so in order to find the total charge, we will integrate, we will integrate Q total is equal to the function for current over all time, which is from minus infinity to infinity, which would be from minus infinity to 0, our current is 0, and from 0 to positive infinity, our current function is 20 e to the minus 5,000 t, and we'll change that t to an x, and dx. All right, so right away we can knock that out. And Q total is equal to 20, we'll bring the constant out, 0 to infinity, e to the minus 5,000 x dx, which is equal to 20 over minus 5,000 times e to the minus 5,000 x from 0 to infinity, which is equal to 20 over minus 5,000 times e to the minus 5,000 times infinity minus e to the minus 5,000 times 0. And we know that e to the minus infinity is approximately 0, and e to the minus 0 is 1. So our Q total is equal to 20 over, so we'll simplify that a little bit, 22 over minus 500 times 0 minus 1, which is 2 over 500, which is 0.004 coulombs. Okay, but the problem statement asks that we express it in microcoulombs, so we know that 0.004 coulombs times in 1 microcoulomb, we have 10 to the minus 6 coulombs, and that would give us 4,000 microcoulombs. And there we have the total charge accumulated over this terminal over all time. Or I should say not accumulated, but entering. So it's coming into that and it's exiting here. Okay, one more problem. Assessment problem 1.4. All right. The expression for the charge entering the upper terminal. Again, upper terminal is terminal 1 is such. Find the maximum value of the current. Okay. Couple things. One, current is equal to dq over dt. And 2, we can find the maximum value of current by integrating our current function and, oops, not dq, and setting that equal to 0. And that will give us the time when current is max. Okay, so first let's find the function of current. So I is, and it's a, we can say I of t is equal to the derivative of 1 over alpha squared minus t over alpha plus 1 over alpha squared times e to the minus alpha t. So that would give us the derivative of a constant is 0. And the second part here is a product, so we'll use the product rule. Let's find the derivative of the first one, which is 1 over alpha and times 1, and this is, so that would be e to the minus alpha t plus t over alpha plus 1 over alpha squared times minus alpha e to the minus alpha t. And let's multiply that out. So we have minus 1 over alpha e to the minus alpha t plus t e to the minus alpha t plus 1 over alpha e to the minus alpha t. And these guys cancel out. And we are left with I of t is equal to t e to the minus alpha t amperes. Okay, so that's our expression for current. Now we want to find the maximum value, so we need to find the derivative of current and set it equal to 0. So the derivative over time of t e to the minus alpha t is equal to 1 times e to the minus alpha t plus t times minus alpha e to the minus alpha t, and that would give us e to the minus alpha t minus alpha t e to the minus alpha t. So e to the minus alpha t is equal to, we're setting this equal to 0. E to the minus alpha t is equal to alpha t e to the minus alpha t. And this and this cancel. So we have 1 is equal to alpha t. So that tells us at time t equal to 1 over alpha, current is max. So let's substitute this value for time into our current expression. So I of 1 over alpha is equal to 1 over alpha e to the minus alpha times 1 over alpha, which is equal to 1 over alpha e to the minus 1. All right, and the problem statement states that alpha is equal to 0.03679. So 1 over 0.03679, and e to the minus 1 is equal to 0.3679. So we will multiply that. And I at 1 over alpha is equal to 10 amps. So our maximum current is 10 amps. And that concludes this video.